Awesome. Thank you very much for that intro. So I'm Michael Freyberger. This was joint work with two of the primary authors of the original implementation of ShadowCrypt, Warren and Dada, Michelle Mazurek from University of Maryland, and my advisor, Pratik Mittal. A little bit about me, since I am not currently a graduate student. This was my senior thesis work during my undergraduate at Princeton University, which I completed in 2016. And for the past 2 years, I've been working at AppNexus as an engineer, and I really like to wear hats. So the motivation for this work is that user-provided textual input should be hidden from web applications. So we talked about secure messaging this week, and when people are communicating back and forth with others, we want that to be secure. But there are plenty of applications where you're more or less communicating with yourself with a few extra features that are offered by the web app. So for instance, when I'm using a calendar application, I'm typing in the title, but Google really never needs to know the title of my calendar, like an event, in order to have a correct functionality. And there are a bunch of other applications like this. So to-do list applications, when I'm creating a to-do list, really all it is me talking back and forth with myself with maybe a checkbox for complete or not and a due date. Similarly, calendar applications or sort of online notes or journals where you're maybe tracking what you did that day. An important note is the applications still need access to metadata, such as whether or not a task was complete, the due date of a to-do list item, maybe the start time and end time of something on your calendar. But these applications do not need any textual input. A calendar doesn't need to know the title. A calendar app doesn't ever need to know the meeting notes for that particular event. So ShadowCrypt, in 2014, they published a paper at CCS where they attempted to provide a solution for this. So they wrote a browser extension that would scan the page for all of input nodes and transform those input nodes into secure input nodes. And what I mean by secure input nodes is they were utilizing the Shadow DOM, a new primitive that came out to browsers probably around 2013, 2014, that allowed for a separation between client-side code and then potentially where the data is actually rendered. So from a user interface perspective, what would happen is if you had a web app where you're about to type in your homework for that week, if you were using ShadowCrypt, instead of just having a plain input, it would look something like this. The user would be able to see, oh, this is secure. And what's happening under the hood is ShadowCrypt is parsing the DOM, and they're finding all of the input nodes, and they're also finding all of the output nodes that have a ShadowCrypt fingerprint. And they're taking those input nodes and they're attaching a shadow tree. And in that shadow tree is where the user will actually interact. So when a user is filling in their homework for that week, they'll be interacting with that bottom blue square, and the gray square, which the web application actually has access to, would only see the ciphertext. And all the encryption would happen within the shadow tree. And similarly, for any output, ShadowCrypt would recognize, oh, this was encrypted. Let me create a shadow tree in order to do the decryption and actually display the plain text. So that's what ShadowCrypt does, and our paper is attacking ShadowCrypt. So we have a UI-based attack, and as well as a Shadow DOM penetration attack, and I put attack in quotes for reasons that I'll explain later. The UI-based attack. Some fundamentals of the attack is that the attacker is the web application itself. So I, as a web application, am aware that users are potentially using ShadowCrypt. All of a sudden, I'm not getting access to all these calendar titles that I want to share with data brokers to get more ad revenue, whatever it may be. So I'm like, oh, I don't want ShadowCrypt, so let me add code to my client side to be able to prevent ShadowCrypt from working. And so that's exactly what ShadowCrypt is doing. They're trying to update their client-side code such that they can actually gain access to this user-provided text. An important note is that this attack must be stealthy. You can imagine an attacker could pretty easily do some sort of DOS attack. A simple DOS attack would be finding all of the elements, or even they could, on their API level, if they ever get an input with some ShadowCrypt fingerprint, they would easily be able to potentially just delete that and just not allow users to use this. But users would pretty quickly realize, like, oh, this website is fishy. Why are they not letting me use this browser extension that's providing me security? So as an attacker, you need to be stealthy such that the user freely gives you the information. The user thinks ShadowCrypt is working when in fact it is not. So what we did is we built a web application. We built a to-do list application that a user could use. We then updated that client-side code such that we were attacking it. And then we validated that attack through a user study to figure out whether or not a user could actually tell if this application was attacked. So to go through our user interface attack, I want to highlight the different steps of what ShadowCrypt actually does, and then how we sort of systematically took them down one by one. So the first thing ShadowCrypt does, as I said, is it will transform all of the editable content fields into secure input nodes. And so naturally, if I am the website owner and all of my input nodes are always secure and I'm never getting access to plain text, I can't actually execute any sort of attack. So the first step is getting an insecure input node onto the page. And by that I mean I need to bypass the ShadowCrypt's input detection. If I can have something on my page that ShadowCrypt doesn't think is an input, they won't actually attach a shadow tree, and therefore I can gain access to the user's plain text. So there are a few different ways to do this. The simplest way is just that ShadowCrypt isn't actually looking for inputs with type search or type email. There's actually important reasons for them doing this is because, as we talked about earlier, search is actually very hard to search encrypted data, and so therefore ShadowCrypt doesn't want to decrease the usability, and so when someone's entering in a search bar, they're like, oh, we shouldn't encrypt that because they should probably send that to the browser, send that back to the application in plain text when they're doing a search. So they don't actually ever detect search nodes, similarly email nodes, because it would be very hard to log in if you once registered with an email in plain text, and now all of a sudden you're registering and trying to log in with an email that's encrypted. Also, it would be very hard to get that first email to confirm your identity. So you don't want to be encrypting email stuff. Now, you could think, let's just have ShadowCrypt have a few more false positives. Maybe the user can like select themselves. Okay, let's turn that off. But they're sort of right now going on the side of we'd rather not have any influence in usability, and they don't want to decrease the usability of the site. So another way to do this is there's some DOM events they're currently not listening to. I could just set up a checkbox input field, and they naturally wouldn't do anything with that because checkboxes are just binary on and off. And then I could just write a script, change the input type to text after the fact, and they're not detecting that DOM event. Pretty easy for them to just patch that. The last one, which would be really, really hard to do in order to actually ever mitigate, and this is a really strong attack, is that a lot of websites aren't actually using just standard inputs like the HTML type. They're using input-like elements. So Google Docs isn't just one massive input. It's like a very complex structure with a bunch of event listeners registered on keystrokes, and it'd be very, very difficult for any sort of implementation that's trying to provide this to actually take all that and then effectively re-implement everything inside of some shadow tree-like element. So we can be pretty confident the attack can get past this and can actually bypass ShadowCrypt input detection. So all we've done so far is gotten an insecure input node onto the page, but that's really not great because the user would pretty quickly realize like, oh, why doesn't this look the way I would expect it to look? Because ShadowCrypt provides this nice UI, and they have this nice lock, and they have this nice border with a color, so I as a user know there's nothing fishy going on. And so I as an attacker naturally need to mimic that secure UI, so the user thinks it's working. Now, mocking the UI would actually be pretty complicated. The lock has some fancy JavaScript on hover stuff. They have really nice animations. I didn't want to try to mock that. Also, like there could be this color. I didn't actually know the color of it, so therefore it would be really hard to guess that color correctly. And also, if they change their UI ever, it would be really hard to maintain the attack. So it'd be much simpler if I could just render an insecure node directly on top of a secure node such that the user thinks they're interacting with a secure node when really they're not. That's a much simpler way as an attacker. It's just a few lines of JavaScript rather than a lot of hair nesting. So what I did, it looks like this. Sorry if you can't read this, but I'll explain every single element. What we have here is on the top this attacker input, which is type search, which ShadowCrypt doesn't ever detect. And then below that is the actual input with type text, which ShadowCrypt actually sees, and they thankfully go ahead and give me this beautiful UI, and then I just smack my insecure one on top of it, and I can just use CSS to make sure that it's on top using like Z indexing. And now, when a user clicks into it, they're clicking into my input, which is not secure, and it looks just like ShadowCrypt is working. This is great. Now it's pretty stealthy. There's a few more though. ShadowCrypt provides some sort of like, almost like a challenge to the attacker in a way. When a user clicks into this, the ShadowCrypt border will become thicker. And so I, as an attacker, then therefore need to mimic that because I don't have access to their CSS code. It's living in the shadow tree. So it's like, well, this isn't good. So what I'll do is I'll just render a colored rectangle and put it in the right place. I know exactly the width of this input, and I can just put that colored rectangle directly where it needs to be. Now the issue is I don't actually know the key color. The key color is a user-provided field that all of the key options are stored locally in local browser storage, and I don't have access to that. Thankfully, it's only 1 pixel, and I'm sure no one in here can tell the difference between these two pictures. The top is a 2-pixel green border, which is benign, there's no attack, and the bottom is if the user had a green border and I just naively guessed a purple border as the color, and you know what, I got it wrong, but I'm pretty confident users won't be able to tell. And so now we're doing pretty well, and the last one is actually a really tough one for me as an attacker, is that ShadowCrypt provides a keyboard shortcut which allows for input in a pop-up window. So some more details on that is we have ShadowCrypt, when a user hits control backtick, it will pop up this window where a user can input. And on that window, it's really important. See the highlighted area there is this passphrase. So similar to how a user can select a color, they can also select a passphrase. And that's anything. Color, there was only 6 options. Passphrase, it's infinite. A user can type in anything. And I don't want to go about trying to guess this passphrase because I'm pretty confident I'll get it wrong. And therefore, what I'll do is if the user ever hits control, I'll just turn my attack off. I'd much rather not be detected and only get a percentage of input than ever be detected. So that's exactly what I'll do. I'll just be like, I don't know the passphrase. Let me just turn the attack off if I see a control key. So we're doing pretty well so far, or at least I think so, but that's not actually convincing necessarily. So we put a user study on Mechanical Turk, and basically the steps were, first we would have the Turker become familiar with this to-do list web application which I created. It was more or less just the standard Meteor to-do application, so I didn't have to write much code. But users aren't familiar with this. I want them to become familiar with the application so they have a knowledge base of how this actually works. Next, they become familiar with ShadowCrypt. I created a video where I explain exactly how ShadowCrypt works. I explain how all the options work, how to set up the options, so that the Turker isn't naive. We try to give them as much knowledge as we can. So this is a more conservative approach because most users wouldn't really know all these options, but we try to be as conservative as we can so the user knows ShadowCrypt. And lastly, we show an experimental version of the web application to this user, and there's a 50% chance of the application being attacked. Our study involved 105 participants. 46 participants were in the control group where the application wasn't attacked, and 59 participants were in the experimental group. So our results. Only 1 out of the 59 people noticed the attack. This was pretty good. I was expecting this because you would have to change the color and you'd have to recognize that color was different. And then the other part is we turned off the attack whenever they used that really secure input node, and so I wanted to see how much of this plain text did I actually capture. And so 92% of the inputs were just inputted plainly. They weren't using the more secure input node. 8% were, but still as an attacker got 90% of the text provided by my user, so I'm feeling pretty good about that. So what are our insights here? The biggest one is detecting and alerting users of this UI misbehavior is really important. The authentication mechanisms that were put in place by ShadowCrypt, they were either easily mimicked or they were just too difficult to use as a user. So as a user, you weren't going to use that control tick very often. You just want to be typing in content. So therefore, they were never really using that. And therefore, I was able to gain access to a lot of the plain text information. Another really important one is privacy systems should really not rely on passive in-content indicators. Users are very prone to ignore these, not really know what they mean. And so it'd be much better if we had systems that could detect these sort of DOM overlays. All I did was simply put something on top of something else, and that really shouldn't be allowed. And so we have some promising work right now that was put out a few years ago by Kaminsky called Ironframe, which is detecting these DOM overlays. And it would be great if we could really alert our users, rather than having something that's always either red or green that they should be looking at to see if something sketchy is going on, really bring it to the forefront for users to know that there's some UI misbehavior going on. Now, all of this attack assumed the shadow DOM was actually secure. And so did I actually need a UI-based attack, or could I just go right through that shadow DOM boundary? So I come back to this slide I had earlier, which supposedly said that I, as an owner of the application, can't pierce down into those shadow trees. So pretty quickly, I just wanted to test that out, and that was not true at all. I very easily was able to just access directly through down to the shadow trees to get the plain text information very easily. Now, that's nothing to say against ShadowCrypt. The important thing here is Shadow DOM is not a privacy primitive. It was implemented to make UI developers' lives easier, and so therefore, it has changed over the years. Client-side code can access this stuff very easily now. And when it was written back in 2013, ShadowCrypt implementers were actually be able to create that secure boundary, but since the spec has changed, it is no longer actually able to secure that boundary. So what we need are privacy-enhancing browser primitives. We need something that can actually provide an impenetrable barrier between application code and the content that the browser is rendering. The closest thing we have right now is an iframe, so you could think of, okay, maybe we can have an iframe-based solution that actually provides that really strong barrier, but iframes have a ton of limitations. As I said, they need to decrypt all of those output elements. So if you have a to-do list with 100 things, that's going to be 100 iframes. The performance there is going to be seriously limited, and so we need a more dedicated browser primitive that can allow for client-side code to be disconnected from the content that's actually being rendered by the browser. So last slide here, key takeaways. I think the most important thing is just recognizing that this is pretty important. I think we're so constantly talking about secure messaging, which is definitely really, really critical. And I think potentially the next step is some of these applications where you're effectively just talking to yourself. So to-do lists or calendar applications or different online note applications, such that we can have secure input-output systems on browsers. Secondly, UI attacks must be prevented actively rather than through passive indicators, and we really need a secure I/O system that's backed by dedicated browser primitives rather than trying to allow for privacy system engineers to just be sort of trying to hack something into something like the Shadow DOM when it really wasn't fit for that. So the user study with all the questions I asked are online, as well as the code for where I attacked this to-do list application. Thank you very much, and I'm glad to take questions.
Questions?
So does the website you're visiting have to know anything about ShadowCrypt?
Yeah, so the website I implemented definitely knew everything about ShadowCrypt. ShadowCrypt is an open
that's
source.
in the attack, but
Yeah.
normal use of ShadowCrypt.
Normal use, no. It's a browser extension, and so like you could install it now, and you could go on Facebook, and all the content you write would become secure.
So how does ShadowCrypt know that, like, if you type something on Facebook, say, it's gonna end up encrypted, and then when it shows it back to, well, if it shows it back to someone else,
it would show
it would be encrypted.
It would be encrypted, correct?
So back to me, ShadowCrypt looks at all the text field, like all the text rendered on the page for some I am encrypted tag. I see, and decrypts it, but only for you.
Exactly. That's how it works. So naturally, that little flag, pretty easy for an application to DOS that. Just be like, okay, ignore all that stuff to prevent users from using it.
Right. But even applications that, like, if the text is this big and it expands when it's encrypted to this big, and the application has something like show the first 20 characters, then ... right?
Yeah.
Then you won't be able to decrypt it, and you won't even see the first 20 characters of plain. So it might break some applications.
Yes, yeah. And ShadowCrypt definitely. The original paper went through a lot of usability studies to see how it worked on sites like Facebook, Twitter, Reddit, and they have some good results in their original paper to show usability to not degrade. Regarding like sort of if you wrote something on Facebook and a user wanted to see that, they sort of punt on key management, and they sort of say users will sort of have some offline protocol to potentially share keys, so that if you were using Twitter and wanted to have your tweet only shown to your 5 close friends and not your entire follower list, maybe you'll use a particular key that you have known to share with those 5 people. But the paper in my work didn't really go into key management and how that would work.
Thanks.
Yeah.
Thanks. It's an interesting paper, interesting concept. I'm wondering, back in the early 90s, there was a whole bunch of research that went on in the concept of trusted path, and even earlier than that, but in particular, in the early 90s, there was a whole bunch of publications around trusted path in graphical user interfaces. And I'm guessing you haven't read that literature. It's not online, and a lot of people believe if it's not in Google, it doesn't exist, which is unfortunate in our academic world. But I wonder whether it might be worth going back and looking at lessons learned from 30 years ago, because we were asking the same questions 30 years ago in the context of Sun windows and X windows and things like that.
100%, totally agree. And I think that what I'm trying to do here is just sort of provide some insights from what I got from doing this attack, and combine that with insights that were from 30 years ago, and hopefully we can have a solution.
More questions? I have a small question. How did you ask the users, what was the question you asked to the users? Did you tell them, can you tell if something is weird? Or did you tell them, do you think ShadowCrypt is working? How do you?
Yeah, I can get the exact wording. It is on that link.
Yeah.
I believe the wording was along the lines of like, was ShadowCrypt working properly?
Was ShadowCrypt working properly? You have a question?
I'm curious about your second takeaway, since it was kind of glossed over a little bit. How did you come to this conclusion?
Basically the fact that the primary way for a user to think ShadowCrypt was working was just seeing that lock icon and seeing that initial border color. But that's very passive way. There was There was no way where ShadowCrypt was actually being able to alert the user like, oh, something is currently on top of the secure input node. It was just assuming if you see this, the user should trust that it's secure. And so those kind of passive indicators are going to be really hard. Users will just assume things are working. And so it'd be much better if the system were able to actively detect this and bring it to the user's attention that something's wrong.
I think we're thanking the speaker again. And
great.
next one. So next, Matthew Smith from the University of Oxford.